Okay, so thank you very much for the kind introduction, Rüdiger. And in the next half hour, I want to give you a brief taste of the kind of work we do at the Realistic Graphics Lab. And this is actually not standard CS material, so I have to give a bit of context and first explain at a high level what rendering is, what inverse rendering is, and what they're good for, and then we'll kind of dive into the technical aspects of the problem. So it'll be a lot of results up front, which is a bit of an unusual ordering. So let's actually begin with the concept of a rendering algorithm. This is a computer program that takes a three-dimensional description of a world, and then it does some calculation, and it turns that into an image, hopefully a photorealistic one. And that all works surprisingly well these days. In fact, we are surrounded by renderings all the time, and usually we don't even notice it. When you watch TV, or when you browse catalogs or magazines, or when you go see a movie, much of what you see isn't real, or only partially so. And that actually makes a lot of sense. I mean, filming a post-apocalyptic film with monkeys as actors, that doesn't sound like such a good idea. And when IKEA already has perfectly good 3D models of the furniture they build, like, why would they make a kitchen with it and then take a single picture and break it all down? That would be really wasteful. So how do renderings achieve this amazing degree of realism? I'm going to explain this to you using a picture that I took on my balcony. So here we have sunlight that's streaming in from the left side, and you can see how some of that sunlight hits this red book and then actually takes some of that color along with it. And lots of other stuff is happening as well. This glass picture refracts some of the light into these interesting patterns called caustics, and then some of the light that enters the milk undergoes thousands upon thousands of little refractions inside this, and that's caused by these little fat bubbles, and that gives milk its delicious glow. If it wasn't for that, milk wouldn't look delicious at all. It would look like white paint. And on top of that, there are some imperfections, scratches, dirt. And our brain is hardwired to see all of these things around us all the time, and we kind of need that to actually consider something as realistic. Like I mentioned at this point, all of that works extremely well, and an image like that is actually well within the capabilities of nowadays of rendering algorithms. Now, one thing that you can observe when looking at this picture is that there are all of these lines. Is line segments, actually. And what each does here is that it shows you how some of the light was transported from point A to point B, and then something happened. The light kind of bounced off an object, and this is called scattering. And this happens over and over again. For example, the details of the next segment are related to the properties of the material there. Is it smooth, or is it rough? Is it metal? Is it glass or plastic? And usually, there are several possibilities that this rendering algorithm has to consider to do a good job. It kind of has to sum over all of the possibilities and the contributions that they make to an image. And in fact, very often, there are not just a few possibilities, it's a whole space of possibilities. And so then, instead of a sum, we need an integral. Okay, but it doesn't really stop there, because this light will actually continue, and it's going to bounce off another object. So there's another whole space of possibilities that we have to integrate over. And so now it's a double integral over two of these spaces of possibilities. And then it'll continue. There'll be more scattering. And I think you can see where this is going. We are going to end up with like an infinitely nested number of integrals over infinitely large spaces. And that's really bad news, because computers are bad at doing computations that take an infinite amount of time. And so the solution to actually make a rendering algorithm finish within a finite degree of time is to use an element of randomness. And so basically, whenever we encounter such an infinite set of possibilities, we randomly pick one of the possible ones. And this is how rendering algorithms work at a high level. So the next time you see a movie that has some visual effects, think about how every pixel of the image that you're seeing is actually the solution to an infinite dimensional integral over all of the possible trajectories of light that could have taken to end up in precisely that pixel. That's what you're seeing. And I worked on rendering before coming to EPFL, and it's a topic that's very dear to my heart. But this is actually not a talk about rendering. Instead, I want to tell you about inverse rendering. So first of all, what is that, and how is it different? Well, the basic idea is that we want to go the opposite way. And so if rendering converts a three-dimensional world into an image, then inverse rendering starts with that image, and it's trying to find a virtual world that is consistent with what we have seen in these images. And this actually turns out to be a much harder problem, because the physical laws basically tell us how to go from the left to the right, but they don't tell us how to get back. So this is what we'll have to figure out. So this is all a bit abstract. Let me show you an example to make that a bit more concrete. Suppose that we have a bunch of pictures of a chair. And these are really just pictures, right? If you zoom in, you can see the colored pixels that this is made of. But this chair hasn't always been a picture. It was actually originally created in a 3D modeling app called Blender. And the artist who created this chair actually built it from countless little polygons, which is a common way in which 3D models are presented in computer graphics. Now, the colors here are all wrong, because that's really just a visualization of the geometry I'm showing to you. Now, hypothetically, suppose that after a particularly heavy modeling session, the computer of this poor person just went up in flames, and the only thing that's left of this beautiful 3D model are some pictures that they posted on Instagram, which poses the question, could we try to recover this three-dimensional model using only those pictures? And luckily, this is exactly what an inverse renderer does. And so for this, we need some kind of an initial shape, something to start with. And this inverse renderer is going to kind of tweak this object to get it to be more consistent. And so let's say we have absolutely no idea. We just start this with a sphere. Well, when we give the sphere to a rendering algorithm, it's going to produce a picture. It'll be a very pretty picture, but it doesn't look anything like this chair that we started with, right? And so our goal is to make them closer somehow. And this is what an inverse renderer does. And it does it over a sequence of steps. You can see how the surface is almost kind of like boiling. The color changes, the shape changes. Eventually, it becomes more and more consistent with the input object. And in this case, this is specified using 32 different views from different sides. And here's another example with just a single view of a chair on a theater stage. In this case, there really isn't enough detail to recover an actual 3D object, but what if we zoom out and then we realize that this chair actually casts many different shadows? Now, if we replace this chair with a sphere like we did before, then not only is the middle part wrong, but so are the shadows, and this actually provides quite a lot of additional information. And an inverse renderer can use all of that information to find a 3D shape that casts the right shadows, even though it only has access to a single image. And you can see how it's kind of evolving that object here. Now, I should say, both of these examples I've shown you are, of course, completely contrived. This is not really a problem that you would ever encounter in the real world, at least as I presented it. You can think of these as kind of computational games that we play in my group just to test out how different algorithms perform on challenges under very controlled situations. A more realistic example would be that we take photos as an input, so not synthetic images. And then, in this case, we're trying to reconstruct this 3D printed bunny. And you can see how the renderer managed to make a good approximation starting from a sphere. Rendering isn't just restricted to hard surfaces. You can also render fuzzy things, and an inverse renderer can reconstruct those fuzzy things, like volumes, volumetric clouds, smoke, and dust. And let me show you one more example. Do you remember these interesting patterns from the beginning of the talk? These were called caustics, and they're created through the refraction by a glass object. And basically what a rendering algorithm can do is, when you give it a glass object, it will tell you what the corresponding caustic looks like. But an inverse renderer can turn all of these questions around. So you can say, if I want to create a particular caustic, like what is the shape of glass that I need to accomplish that? For example, here we're optimizing a glass panel that refracts light into Hokusai's great wave. And you can see the resulting glass slab. It's a bit hard to see, but there's a fine surface pattern here. This is not perfectly flat anymore. And when you put it into this beam of light at just the right angle, then the image comes out. And here's another type of lens that mixes colored illumination to create a famous painting by Georges Seurat. By the way, this idea of caustic design isn't new at all. In fact, there's an EPFL startup called Waveform by Mark Pauli's group GCM that does an incredible job on this problem using a different technological approach. Now that I've shown you a few examples of all of this, I think you may have spotted certain patterns. We never find the solution directly. Instead, this takes a number of steps. And every time we begin with some kind of a tentative 3D world, we run the rendering algorithm that produces a picture. And then we compare that picture to a reference. And behind the scenes, there is another process I didn't really show you, but basically that gets crunched down into a single number that tells us how close are we. We want that number to be 0, ideally. You can think of each possible 3D chair model as being a point in a space. And this loss that I've shown you, it basically gives us the height of that point. Now, the original object, it really doesn't look anything like that chair. And so that it means in this loss landscape, we're pretty far up. The other thing you can observe is that the slope is pretty steep there. And our goal is basically to kind of ski down this slope, right? And that'll bring us to the solution we are looking for. And so for this to work, the algorithm must know about this slope. That's really a key piece of information. And I'll explain to you how to get that in the second part of the talk. And moving down with the slope information is the basic idea of an algorithm called gradient descent. And the slope of this imaginary hill provides exactly the recipe that we need to update the virtual world. And at this point now, we have a loop, and we just kind of spin around many times. And in case you're wondering about that, in these kinds of results, I've shown you like one going around once might take like a second or something like that, sometimes less, sometimes more. And a full reconstruction is maybe on the order of an hour or a few hours. So it's not for free, but it's also not crazy expensive. If you just have a workstation, you can do a lot, and you don't need like a whole data center or so. If you followed some of the excitement about machine learning in the last couple of years, in fact, this picture will look very familiar to you, because most machine learning tasks are structured in exactly the same way. We have some kind of an input, for example, an image of these cows, and we want to segment that image into different semantic regions. There's a loss. We use some variant of gradient descent. But now all of the heavy lifting is done by a neural network. And so basically the idea is that we teach this neural network how to segment images by showing it many examples of that process. So given that similarity, why don't we just use neural networks, right? The answer is that there are two problems with them. The first is that when you train a neural network, you get a bunch of numbers, but nobody really knows what these numbers mean. And the second is that you have to actually teach a neural network physics for it to be useful, because there's a physical process. And this isn't really crazy physics, right? This is like the physics we're using has been well understood for over 100 years. It makes no sense to try to teach that kind of physics to a neural network and for it to waste time with that. And by applying the mechanics of machine learning to a non-neural computation, not only do we get kind of a recipe where we understand how the solution was obtained, we also get a certificate that basically says, if you take these coefficients that you got and you re-render them with a state-of-the-art physical simulator, you will reproduce your data set. And this is extremely valuable in the kinds of applications I will talk about later. And so because of that, neural nets were basically forbidden in my group so far. That will probably change in the future, because they definitely are useful for many things, and there are also ways of using them in a physical context. But that basically explains why there will be absolutely no neural networks in the rest of today's talk. Now, before moving on to technical details, let me explain to you why I'm really excited about all of this and some things that the future might maybe bring. For example, in the field of daylighting, architects want to make buildings that make better use of natural daylight. And that's both to make the buildings more energy efficient, but also to make them more comfortable for their inhabitants. Could we make an inverse render for architects that kind of takes what they want to accomplish and then it evolves different versions of the building for them? Or let's think more broadly. Differentiable and inverse rendering, that's sort of like a way of taking an image and then explaining how that image came to be as a consequence of physics. And that's actually a very common need in many scientific disciplines that involve any kind of instrument, basically. People look at these images and they want to understand how they were created. And let me give you one example of that of particular relevance. Every square meter on the Earth receives on the average of 340 watts of light energy. And the atmosphere above our eyes looks pretty transparent to us on a cloudless day, but it's actually extremely absorptive outside of the visible range. So about 20% of that energy doesn't even get to the ground. It's absorbed already by the atmosphere. And about 50% gets absorbed at ground level, and then all of the rest gets reflected back into space. This is a kind of a simplified picture. In reality, it's more complicated because we have all of these interactions with ice crystals, water clouds, aerosol. So the actual trajectory that light takes will look much more chaotic. And it's sort of the end result of that process that matters. Either things get reflected back into space, or they get absorbed by the ground or the atmosphere. And that heats up both of these. As a consequence, the planet becomes warm and it begins to radiate thermal energy. Think of like a piece of iron that's glowing red hot. It's that same kind of physical effect. Now, because of the presence of greenhouse gases, what basically happens is that not all of this thermal radiation can escape out into space. But because greenhouse gases are absorbed exactly at these wavelengths of the thermal radiation, some of it gets absorbed and it contributes further to heating of the atmosphere. And so you can see here that global warming, which is an effect that concerns us all, is to first order really something that boils down to absorption or scattering and that we can model by simulating light. And to begin to make heads and tails of this, we have satellites that are observing the planet at many different wavelengths, for example, those of the EU Copernicus program. And you can think of such a satellite as a fancy camera that takes a picture with many color channels. Now, the tricky bit is that this camera doesn't give a picture containing the information needed by climate experts. It gives you just, more like when you take a picture with a normal camera. All the information is mixed up with each other. In fact, it's really a little bit like this motivating example that I've shown you before, where this laptop was kind of looking red, even though it's actually not red. It's red because of something else in its neighborhood. So we have to kind of untangle all of these different effects to get a handle at the actual things that are interesting. And inverse rendering is exactly that. It's a tool to unravel these different light effects to get to physical quantities, and I think one that will play a role in the future. And the connection here has been noticed by others as well. For example, the EU Copernicus mission actually funds the development of a piece of software called Irradiate. That's a atmospheric simulator, and that is actually built on our lab code base that we developed here at EPFL. So at this point, I hope that I've convinced you that this is an important problem. Now let's talk about how to solve it. So we've been working on inverse problems since 2019 on a sequence of interconnected projects that are roughly split into 3 major efforts. The first one is basically how to make that process efficient. And the second one is how to deal with a mathematic degeneracy related to discontinuities. And the last one is to build compilers that drive this underlying computation. And I'm going to show you a glimpse of each of these 3 efforts. And for the first one, we have to go back to the motivating example with the skier. So the key piece of information we need is the slope of this function. This is the derivative. And so because of that, these algorithms are often called differentiable rendering. And in higher dimensions, the derivative is called a gradient vector. And so basically what we need to do is to run the rendering algorithm and then get its gradient. And that turns out to be a completely standard step. So many people need that. In fact, anybody doing machine learning needs gradients. And there are these amazing frameworks like TensorFlow and JAX and PyTorch. And they even do that automatically for you. So we will simply use one of these frameworks. That's it. Thank you for your attention. I will take questions now. Actually, I'm kidding. It doesn't work. So these tools immediately run out of memory and crash. And even if you could run them, they would give you the wrong answer. So I will first focus on the memory issue, and then we will talk about why they are wrong. So let's think about the memory issue. How do they work? if you do an operation like a multiplication on one of these tools, they have to keep track of that. So if you multiply two numbers, they're going to create a node in a graph. And then if you continue that calculation, they will add to that graph. And then at the end, when we do a gradient computation, we basically do a reverse sweep of that graph. That's why it's called backpropagation. And this reveals an elementary ordering conflict, which is that the computation goes from the left to the right, but backpropagation goes from the right to the left. And that's a problem, because it now means that we have to remember all of the steps of this calculation to be able to get the gradients. And this works perfectly fine if you're doing machine learning, because you have a pretty simple computational structure with these really expensive operations like matrix multiplications, but you don't have so many of those. But rendering is nothing like that. The graph gets really large and messy. Even me just trying to show you what one looks like is a tremendous technical challenge. So what can we do to fix that? Before we get to the fix, I have to explain a little bit more how a normal rendering algorithm operates and the equation that it solves, which you can see here. You should be able to see this little black dot that's moving on the ceiling, and on the right we have the corresponding calculation, basically to compute the pixel color of that black region. It's a spherical over all of the light that's arriving at this black dot, and a function describing the material. Now, in this case, this is sort of like a metallic ceiling, and you can see the effect of the multiplication of these two functions, which is that it selects out a small part of the incident illumination. And that's what's giving us this mirror-like reflection. Kind of makes sense. And here's a more complete version of this equation. It gives the amount of outgoing light at x into a direction of omega, and that's composed of a sum of two things. First of all, there could be emission. Like, what if this table is on fire? Then it'll emit some light, okay? And then the other thing that could happen is some light, maybe it comes from somewhere else, and then it bounces off that table. And that's what this integral specifies. The reason why we have an integral is because we need to consider all of the different directions from which light might come. And when you have an equation like this, actually a perfectly valid thing that you can do is you differentiate it. And I will do that now with respect to some arbitrary parameter out of the millions and millions describing this virtual world, and that'll be this green symbol. Now, this produces a new equation, and this, you can actually try to interpret this equation physically. So we're still looking at this table, but now we have magic goggles that reveal a new type of radiation. This is derivative light. And so what this equation is now saying is that this table actually emits derivative light if it's on fire in a differentiable way. So what that means is that this parameter theta, for example, controls the color of the flames. Then that will emit this new and strange type of radiation. Now, the second part of that equation was an integral with a product, so we have to apply the product rule, which means now we get multiple terms. The first one is saying that when normal light arrives at this table, and when that table has differentiable parameters, then it's going to convert some of that light into this new and strange derivative light. And then the last one says that when we have derivative light that's coming from somewhere else, then it bounces off the normal way, according to regular physics. And so TLDR, we have actually just found a physical interpretation of the act of differentiating something, which is that everything turns into a light source and it emits derivative light. And then once this derivative light is created, it obeys regular physics. It would seem that we could just sit down and implement this now, but it's actually not enough. We need more things. It's ingredient number 1 of 3, and ingredients number 2 and 3 are symmetries. The first one, or the second one, is a physical principle called Helmholtz reciprocity, which says that when you have a sensor and a light source, then you can flip them, and it doesn't change the measurement. And the third one is that when you have arithmetic operations, then these are also coupled with associated inverse. So in a limited setting, sometimes you can turn these around and then run a calculation backwards. And by combining all of these 3 different steps, we were able to turn differentiation into a physical process that can be efficiently simulated. And now every gradient step has 2 parts. First, we perform a normal simulation that produces an image, and then we perform a simulation of this derivative light, and that produces a gradient vector. Now, if we had implemented our rendering algorithm on PyTorch, and if we had an infinite amount of memory, then that second step would have actually happened kind of on its own, because the tool will build this computation graph, and then traversing this computation graph, it's kind of equivalent to doing this. And sort of the key thing of this discovery is that we actually don't need the computation graph. We can just directly do that simulation, and this leads to huge speedups approaching a factor of 1,000x. So that's that. Next problem, discontinuities. Imagine that we're computing the derivative of a rendering, and we have a parameter theta that moves the chess piece. And you can see an example integral on the left. Now, a rendering algorithm, the way it's going to try to compute that integral is that it'll pick a lot of random points on the domain, and then it's kind of going to average the function value there, and that gives us an approximation of the value of the integral. Now, the problem is that in physical worlds, we have objects and they have boundaries, and that creates discontinuities. You can see these discontinuities here, right? And now if our parameter theta moves this object, then you can see that that actually causes like some of these discontinuities to move over these green points, and that actually completely breaks this process of differentiation. It's going to give us the wrong answer now. And we've explored different ways of fixing them. There are all kinds of things that you can do, but for example, one way to do it is that you actually, like you change the coordinates of this integral so that the green points slowly follow the motion of this object, and then that whole problem doesn't even arise. And here you can see how that matters. This is the derivative of a rendering, so it looks a little bit weird. Basically, the bunny is moving towards the left, and if a pixel is red, it means that that pixel becomes a little bit brighter, and if a pixel is blue, it means that it becomes a little bit darker. And you can see kind of the naive way where we just differentiated and we didn't think about anything special, and then there's the corrected version at the bottom. And it seems really minor. I mean, if you pay very careful attention, you're going to be able to see some differences, but in general, it looks almost the same. You might be tempted to say, I will just ignore this. But let me show you what happens when you then try to reconstruct an actual object using these derivatives, the bunny in this case starting from a sphere. It's very disturbing what happens with the naive version, so we definitely don't want that one. Let's talk about the last part, systems. So over the last years, we've created our own compiler, which is called Dr. JIT. And Dr. JIT turns simulations into efficient CPU and GPU code, including hardware-accelerated ray tracing and these kinds of things. This logo has a medical connotation. It was kindly designed by my father. And this is actually related to our own mental health that was at stake before we had this compiler, because it was really difficult to do things prior to that. Now, this is a systems project, and there are so many nitty-gritty details that I don't have time to talk about. But what I want to tell you is like why we built a compiler, because it's just such a strange thing to do. A compiler takes different objects like cameras, light sources, shapes, and that leads to a blueprint. The scene is a blueprint basically for combining all of these different types of modules. And you can see an example scene like this here. And then when we perform the simulation, they are talking to each other through function calls. But we don't want to render, we want to compute the derivative of that. And so extra stuff has to be computed. And those derivatives also have to be propagated across these function calls. But this is actually a quite naive way of thinking about the problem, because oftentimes there are certain elements that don't need to be differentiated. And even within these boxes, there are just a subset of the computation that can actually influence the gradient. And the tricky thing is basically that you can only know about this stuff once you've actually seen the 3D world that you want to optimize and you know what the user is trying to do. And because of that, we had to build a just-in-time compiler for that problem. Another curiosity is rendering, is polymorphism in rendering. So when light encounters an object, then what actually happens really greatly depends on, for example, what the object is made of. And then at an implementation level, what it means is that you have a huge program, you're executing line after line in that, and suddenly you have to jump to one of many other places and then kind of jump back. And these indirect calls are all over the place. So it's really crucial that we can not only do them efficiently on GPUs, but also differentiate them. And the resulting tool is the foundation of Mitsuba, our in-house renderer. We spent quite a bit of time on engineering this, documenting it, making it easy to use. We're actually a little bit like a software company with a product. So that means that PhD students sometimes have to write test cases and documentation and things like that. And that brings me to the end of the technical bits. So during all of this time, I've been really lucky to work with an amazing and talented team of PhD students, postdocs, and engineers. And I especially want to thank my first generation of PhD students who put up with me while I was still learning this professor thing. And the projects you saw are really gems, I think, all incredible individual achievements of different team members. And it's a testament to their creativity and their drive, how far things have come along. I also really want to thank Pauline, who takes care of all of the administrative parts and shields us from a lot of that. And she manages to always do it with a smile and is attentive to so many other needs that we have. So this is great. It just makes life that much easier. And I'm lucky to also have a loving and supportive family. They give me strength and happiness. And I'm really glad, actually, that they could all come.